Thank you. So let me start by thanking the organizers for giving me the opportunity to present this work. It's a great pleasure to be here in Vienna and present some aspects of work I did in collaboration with Saskia Demulder and Dieter, and actually also some work in progress. So it's not a surprise for us all that by now we know that quantum gravity is in some sense very special. And not everything that looks consistent from a low energy perspective, low energy effective field theory perspective is actually valid if you want to couple to quantum gravity. And of course, the theories that can be coupled to quantum gravity in a consistent way are the lay in the landscape, while the rest of them, we put them into Swampland. And then the Swampland program is in some sense, of course, the ambitious projects on finding criteria on how we actually put these theories, separate them from the landscape from the Swampland. And this is done by defining a set of conjectures. And there is a quite big net by now of different conjectures, but I want to actually focus on the distance conjecture today, and also in the second part on a related cousin of it, the Ricci flow conjecture. Without spending too much words, let me quickly recap the distance conjecture as formulated by Uguri and Waffa. So we have our modular space, and when we go to large distances in this modular space, we expect an infinite tower of massless or exponentially light states that invalidate our effective field theory. And what is the prime example of this? It's basically the circle and the trivially fibered circle example. So after reduction, we get an action from which we can read off the distance on a modular space. And we see we have, after canonically normalizing, we have two infinite distance points that R is 0 and R is infinity. And we know the associated infinite towers given by the KK tower and the string winding modes. But what is even nicer in addition is that we also have T-duality. So even if we would have known only one of the two infinite distance points and the towers, we could have immediately said that there has to be another infinite distance point, and we would have known the towers for free, because T-duality inverts the radius, so sends 0 to infinity, and it swaps the winding and momentum modes. But of course, the question is, this is a very symmetric, very nice picture. What happens if we look at T-duality for more complicated examples? We want to swap our internal spaces given by a circle by something that is some curved internal manifold, possibly with fluxes, some non-trivial circle vibration. And then, of course, since we have curvature and fluxes, we will get the scalar potential. And let me already say I use the word modular space and scalar field space equivalently. So, and then on the T-duality, since we now have spaces that have a non-trivial topology, actually, in contrast to the local Buscher rules, T-duality has also a global perspective. Namely, it can change topological data with fluxes. It can interchange the first Chern class with the H flux. And if we have enough T-duality, what we can also arrive at is so-called non-geometric backgrounds, in particular T-folds that I will comment on later. And we can ask, in what sense do these lessons we learn from looking at the spaces modify the Swampland distance conjecture, or at least what can we learn from these more complicated examples? And just to highlight the general setup, so I'm working completely in the bosonic sector, only NSNS sector, and we start in some higher dimensional theory with some external space and then n-dimensional internal space. And under some assumptions on the involved metric and fluxes, we can reduce to our low energy effective theory, where we now have a modular space metric that is given, or we can read off from the kinetic terms of the scalar fields and some potential on this scalar field space. And so the general expression for such a metric is then the first part here, the usual DeWitt-like part of the metric. But since for the moment, at least, we are also allowing the flux or the B field to depend on the moduli, we will get the separate second term here that is the analog, the DeWitt-like analog of the usual metric variations, and a scalar potential on this modular scalar field space that is basically given by the internal action. And actually, the properties that are changing now, or the many new features that we encounter, are best described by giving you an example. And the best example to do this is actually the three-sphere with H flux in it. So I'm choosing some nice parameterization of my metric in order to do T-duality on the three-sphere. I view it as the Hopf vibration. and I put k units of h flux on it. And then I can just plug it into my formulas. I get the metric that is very similar to the circle case. I have two infinite distance points, but I also get the scalar potential. And before we discuss these properties, the first thing that I can see that is really different to the circle is that on the sphere, there cannot be any winding modes. So any loop I put on the sphere is contractible as measured by the fundamental group being 0. So this is already a very different situation. So I will see there will not be this nice symmetric interchange of winding and momentum modes under T-duality anymore. And of course, there are now two questions. So how is this absence of these winding modes compatible with T-duality? What does T-duality actually map? We should get consistent pictures on either side of the duality. And what does this mean for the Swampland distance conjecture? So let's first focus a bit on the T-duality. So I told you that I view the sphere as the Hopf vibration, so a well-defined circle vibration, and I put k units of h flux in it. And this, the Hopf vibration has an associated Chern class of 1. And if I T-dualize along the Hopf fiber, I get another well-defined circle vibration. But now I have a fiber that is a circle of the inverse radius fibered over a two-sphere of radius r. And now I have 1 unit of h flux. And this space is actually now first Chern class k. And this is what I was mentioning earlier, that the T-duality in the topological sense for well-defined circle vibrations is actually interchanging this flux with the Chern classes here. And now we see here we have no winding. Here we have also something rather exotic if we compare it to the circle, namely we have winding in ZK, which means that we can wind k times. And if we wind k plus 1 times, the loop gets contractible, so we have only a finite tower of winding states. And now one can go to the exercise and try to match or see if really T-duality properly interchanges the towers, what happens to the abscess of winding modes that will get mapped to momentum modes that are non-conserved, or vice versa, this finite number of winding modes also gets mapped to non-conserved momentum modes. And without going into too many details, this can be summarized by this table. So T-duality is in fact consistent, and also the mass behavior of these towers that gets mapped is consistent within T-duality. So for example, if I go to R is infinity, I have no winding modes, but that's fine because I have my momentum states that become light. And in the T-dual picture, I have also some, I can show that I have some momentum states becoming light. I would have additionally these winding modes that become light, but they are only finitely many. Similar here, everything is consistent, but while we here have a tower of light states, here, clearly, no matter in which picture we look, the winding modes would be the ones that become light, while the momentum modes become heavy. So there is simply there are no towers of states, no modes becoming light. But this, in some sense, could be viewed as an apparent problem because the free sphere with an appropriately turned flux is a valid string background, a purely bosonic one, and it should be in the landscape. So, however, there is no tower of light states as I go to this R to 0 limit. So what happens with respect to the distance conjecture? Well, we didn't take into account one thing, and this is the scalar potential. And I plotted here the scalar potential, and while for R going to infinity, the potential also goes to 0. So this is in some sense fine, and we get the expected behavior. If we go towards R is 0, the potential diverges. And what we now actually suggest to do as some kind of amendment to the distance conjecture is the following. We say, in an effective field theory that can be actually lifted to a quantum gravity, and that is in the landscape, a divergence in the scalar potential emerges when we approach an infinite distance point for which the target space geometry cannot give rise to a light tower of states. So in some sense, the potential signals this pathological infinite distance, or we can say it protects us from going there. However, I want to No, this is a classical consideration. We are not taking into account any corrections or anything, or also no higher curvature corrections or anything. This is for the moment just, yes. But I want to stress that, of course, all of these statements somehow also depends on the fact that we implicitly assume that this is still a valid infinite distance point, that we actually can go there. And I want to put this question to the side for a moment, and I will come back to it later when I discuss some actually work in progress. But before that, I want to discuss some other results that we discussed in the paper. So for that, let me go back to this expression for the metrical modular space that I gave you. So it was given by this sum of traces of the derivatives of the metric and the B field. So I remind you that H is the internal metric. And then we can take an object that is called generalized metric from double field theory, where basically the only important thing is that it's an element in OD, D, and T-duality acts on this generalized metric simply by an ODD transformation itself. And since this is the trace of this expression is invariant under ODD, we immediately get that this whole expression is invariant under abelian T-duality. But why is this interesting? Again, looking back to an example, namely again the sphere, where we now where we set the flux or the level of the associated estimator model to be R squared. So we are on shell, and we're looking at the family of vacuum. And we can apply T-duality, and the dual space, without giving you the explicit form of the metric, the radius, so the modulus, will only appear in the metric, not in the flux. So we can vary the metric in the standard the width-like way. Well, if we look at the dual, which is the sphere with the flux, now we clearly have the modulus sitting in the B field, and this contribution here is non-zero. And we really only get matching expressions of the metric on moduli space, which we want to have since they are T-dual, so they should be equivalent, if we take into account also this variation of the flux. And let me mention that this is in spirit somehow connected to what was done in this paper by Lee, Paltin, Petri, and some follow-up paper, where in the context of ADS spaces, they looked for a positive action metric, and they found that one actually has to include flux variations. However, they looked at Raml flux. And this brings me to the last main point that we looked at in the paper, and this is non-geometric backgrounds. So what are these non-geometric backgrounds? So as introduced by Lavolcar and Hull, and then many subsequent papers, these are described locally by Riemannian geometry. However, the transition functions are also allowed to be T-dualities. So if I look at, for example, on a more standard Riemannian manifold, like the torus, then if I go around the patches, I'm allowed to at most glue with diffeomorphisms. While on these non-geometric backgrounds or T-folds, I can go once around, but at some point, I'm also allowed to glue with a T-duality. So, for example, I'm allowed to jump from a small radius to a big radius. And this is perfectly fine in string theory. The string doesn't care at all because T-duality is a perfectly well symmetry or duality of string theory. So we cannot evade these backgrounds in string theory. We should take them into account. And furthermore, there was also quite some interest in these non-geometric backgrounds in terms of modular stabilization, because these backgrounds, there appear some fluxes that one would usually not get in an NSNS from an NSNS frame. Because, for example, and these fluxes are called Q or even R fluxes. And the prime example would be to take a torus with H flux. And if you T-dualize once, you get some geometric flux that is basically a nil manifold. But if you T-dualize again, you encounter these exotic fluxes that usually you would not see, that are due to this non-geometric, are assigned for this non-geometric appearance of the space. And then, of course, one could ask, okay, are these valid backgrounds of quantum gravity, or how do they fit at least into the Swampland? So the kind of problem in the normal formulation of these backgrounds is that they are somehow ill-defined, that they are somehow ill-defined in the usual NSNS frame. For example, you have some monodromy. If you have a periodic coordinate and you go once around this coordinate, your metric doesn't follow this periodicity. And then, of course, the question is, how can I reduce on these spaces if they are ill-defined? And how do I obtain the metric and the potential moduli space? And if they are T-dual to geometric spaces, I better get matching moduli spaces, potentials, metric, and so on. And there is one key point that was done by these authors here, so Aniola, Force, Dieter, and Patolong, in so-called supergravity, using the so-called supergravity action, or beta supergravity action, sorry. And the key is that one has to do a field redefinition, treating the usual metric for some tilde metric, and the B field, the NSNS2 form, for something that is bivector called the beta field. And doing this, one can show that one can write down a new action denoted by this beta that is equivalent to the NSNS frame up to a total derivative. And then passing, for example, for the expression for the potential coming from the internal space, one would get an expression like this. And this is well defined. This respects all my periodicities. Again, I can do the reduction. And what we found by looking at some examples is that only if you pass to this beta supergravity formulation, you will actually be able to match the moduli spaces, in particular the potential. Otherwise, you would run into some kind of inconsistency. So it's really crucial to utilize this beta supergravity formulation. And while this is the last main result of the paper, and I want to discuss a bit on this work in progress that we are doing now and come back to this question of this notion of infinite distance in the presence of a potential. We take a different perspective and we ask, in which sense is REC, or even at infinite distance point, in the presence of a divergent scalar potential? So in particular, is it even reachable? And what is a good notion of distance? And while there is a huge amount of work looking at how to define distances in the context of the Swampland program, very recently there were two papers discussed trying to tackle exactly this problem. So how to define a notion of distance if I have a scalar potential. But I also want to point out that even a bit earlier by Davide De Biasio, a former PhD student at the Max Planck, he looked at Ricci flow. And implicitly what he did, he also introduced a potential, and in this way tried using Ricci flow to define a notion of distance. And this is what brings me to a somehow alternative approach to these questions, and this is Ricci flow and the associated Ricci flow conjecture as put forward by Georgios Lüst and Lüst in 2019. So what is Ricci flow? Ricci flow is a flow equation, a partial differential equation for my metric that is sourced by the Ricci tensor, as introduced by Hamilton already many years ago. And the Ricci flow conjecture now, as put forward by these authors, says that take a family of metrics that satisfy this Ricci flow equation. Then there is an infinite tower of states becoming massless when you approach a fixed point at infinite distance. And why is this very nice? Because it immediately gives you back the ADS distance conjecture. So if I start with the Ricci tensor, since it's in Einstein space, I can write it like this with a negative cosmological constant, and I can solve explicitly the Ricci flow equation, and I see that I have a fixed point at flat space as I go with my time to infinity. And then, of course, there's the question, well, is it an infinite distance point? There are two ways to look at this. So one can simply take this expression, plug it into the usual width-like metric, and see that it actually goes to infinity. Or, as also put forward by the authors, actually define a notion of distance by taking the log of the Ricci curvature at my starting point and divided by the Ricci curvature as I go to this fixed point. And you can see that this actually agrees. And by this, I immediately get back from this Ricci flow conjecture, the ADS distance conjecture. However, there is even a somehow nicer, mathematical, more interesting distance of notion one can assign. And this is looking at work of Perelman. So Perelman, in his seminal work on showing the Poincare conjecture, he defined what is now known as Perelman's combined flow, which is, again, basically the Ricci flow for the metric, together with a flow equation for a scalar that, in principle, we can think of as the dilaton. And why is this very nice? Because this is gradient with respect to some entropy functional. And this entropy functional is given by this expression f here. So it's basically Einstein gravity coupled to a scalar. And it's even particularly nicer because it is monotonous all along the flow. And then, as again put forward in this paper, one can define some alternative notion of the Ricci flow conjecture, where one defines even the field distance along this combined flow using this entropy functional. And the conjecture is that f is 0 lies at infinite distance and is accompanied by an infinite tower of massless states, where the distance is now given as the log of this entropy functional evaluated at the starting point divided by the final point. Now, what can one do with this, getting back to the question that I asked in the beginning? So this is now some work in progress. I will be rather broad. So can we define a notion of distance for a generic internal manifold using some notion of generalized Ricci flow? And what are the implications for the Swampland distance conjecture in the presence of a potential? And there is actually some very nice work that is already 15 years now again, that generalizes Ricci flow even a step further, that defines an entropy functional that is now basically given as the string effective action of the NSNS of the NSNS sector. And they showed that this is again gives a flow that is gradient with respect to this functional for the metric, the B field, and the dilaton. But at the same point, the metric and the potential that define my distance and my potential on moduli or scalar field space, they are derived from the internal geometry. They are derived from the metric, the curvature, from the H flux on the internal manifold and the dilaton. While this functional knows exactly about these properties, so one can ask, what would be the implications if I define a distance in the presence of a potential by now taking the log of this entropy functional that generates the generalized Ricci flow. And without going into any deeper implications, I want to highlight the following thing. So one can look at the sphere. The sphere under normal Ricci flow flows towards 0 radius. While if I take a sphere with flux and I compute this generalized Ricci flow, it actually stabilizes. It stabilizes towards exactly the point where I am on shell, where I have my radius to be the square root of the level or of the flux. And of course, this suggests a nice, or hints also at, in some sense, towards the fact that maybe one should not go towards this point of 0 radius as suggested by this flow always going, also if you start from a smaller sphere, goes towards this fixed point. And then, of course, there are many other related questions that we want to or are looking into. So can one generalize this to also add Raml fluxes? Of course, if one wants to talk about more general setups, this is necessary. And since this has a very nice formulation in terms of generalized geometry, it seems also very well fit to talk about flows of non-geometric backgrounds. And this actually brings me to my conclusions and a short summary. So I showed you how what are the implications if you look at the distance conjecture with curved spaces and fluxes on it. I showed you the invariance of the modular space metric on the Billion T-duality, this interplay of the scalar potential with the absence of a tower of states in terms of a diverging scalar potential that signals us the absence of these states. And we did a first step towards implementing non-geometric backgrounds into the Swampland program. There are many further steps and directions that we are looking into. So one is, of course, looking at more realistic setups, putting some Raml fluxes and seeing what happens with the potentials that I get there. Are there absent fluxes when the potential diverges? What is actually the importance of looking at off-shell versus on-shell variations and potentials? What this is also related to what was done in these papers that I mentioned earlier. One can look at deformations or generalized T-dualities that generate for me backgrounds with more moduli or scalar fields that are somehow anyway have a clear interpretation. Then this problem of defining a distance in the presence of a potential using generalized Ricci flow, following the ideas put here and also, of course, related to what was here. And then the big question that is somehow the elephant in the room, what is with truly non-geometric backgrounds? So the non-geometric backgrounds I told you about, these are called, these are actually only globally non-geometric, they are locally still Riemannian, but of course there are the truly non-geometric spaces that have not even local Riemannian descriptions, and it would be interesting what one can say about these backgrounds with respect to the Swampland. Thank you.